In this video, we're going to be talking about how we can find measures of angles in inscribed quadrilaterals. So what does that mean? That means that we have a quadrilateral shape that is drawn inside of a circle so that its vertices are all touching the outside of the circle. So there's going to be some unique relationships involving these measures of angles inside. One we already know, if we've studied quadrilaterals before, we know that all four angles are going to add up to 360. So in this first example, we used a protractor and we just went around and measured each of the four angles using the protractor tool and just kind of keeping it simple, not really using like 81 degrees, just kind of rounding to the tens just to make it easy to compare. So we have these four measures here. And again, we know that all four angles are going to add up to 360, but there's another unique relationship that happens when quadrilaterals are inscribed in a circle. What ends up happening is that we have opposite angles that add up to 180 degrees. So opposite angles are going to be supplementary in a diagram that looks like this. So if I have a quadrilateral that is inscribed or drawn inside of a circle, I know its opposite angles are going to add up to 180. However, the converse would not be true. I can't just say that all quadrilaterals have opposite supplementary angles. That's not necessarily true. Just quadrilaterals that could fit nicely inside or be inscribed inside a circle. So let's emphasize that a little bit more on the next page. First of all, we got to be able to identify our opposite angles. If we can do that, then we can set up equations where we add the two measures and set it equal to 180. For many cases, it may be pretty easy to see opposite angles, angles that are across from each other. A and C are not directly across from each other, but they're across from each other enough. If it gets a little more difficult than that, then start to think about it this way. The opposite angles are going to be the angles that are not next to each other. So D and C are next to each other, they're not going to be opposite angles. If I wanted to find the opposite angle of C, I would have to skip D and go to the next one. So A and C are opposite angles. Or if I went the other direction, C and B are consecutive or next to, and I would skip B and go over to A. So because there's only four angles, we can just use that and just skip an angle that's next to it, and the next angle would be the opposite angle. So opposite from angle CDA, which is just angle D right here, would be angle B, or ABC, or CBA. There's three different ways to name that angle. Similarly, angle DAB is just angle A up here, and opposite from it would be angle DCB or BCD, or just angle C. So again, if you can identify your opposite angles, you can set up your equations. Let's do an example. In this quadrilateral inscribed in a circle, we know that angles M and K are opposite, so they're going to be supplementary. But because we don't have any measure for angle M, we're probably not going to want to use that pair to start off with. So let's look for another opposite pair. We also know that angle J and L are going to be opposite. So since we're given their expressions, we can use those. We can add them together and set it equal to 180. So combine your two opposite angle measures, set it equal to 180, and then solve algebraically for x in this case. We get about x equals 10. So then we could plug that x value back in, and we could solve for angle L. We could plug it in over here and solve for angle K, and we could also plug the x value in up here and solve for angle J. So doing that gives us these three measurements. And then we may still be stuck. How are we going to solve for angle M? Well, we just go back to that property. Opposite angles are supplementary, so if we know angle K is 60 degrees, its supplement is just 120. So the measurement of angle M is 120. Here's another example to do. Again, we're just doing the same thing. We have a quadrilateral inscribed in a circle. So the theorem that opposite angles are supplementary is going to be true. Let's find two opposite angles that we're given information for that we can use. U and W are opposite, and we're given both of their expressions. So let's set up that equation. Adding those two expressions together, combining like terms, setting it equal to 180. And solving for z, we get about 8. So we can plug that z value back in and get our angle measurements, plug it into w, plug it in up here for the measurement of angle u, and then one more time over here for the measurement of angle t, and get our 3 angle measurements there. One thing I didn't mention that we could have done on that last example, and we can do it on this one as well. We know that all 4 angles are going to add up to 360, so you could take those 3 angle measures, add them up, and subtract that sum from 360 to get your last angle measure. That just seems to be more work than what's necessary. If we know that opposite angles are going to be supplementary, then we can just find the measurement of angle t, and then subtract that measurement from 180 to find our supplement for angle v. One more thing I just want to point out is that while it is true that all 4 angles of a quadrilateral add up to 360, there are some cases, some examples where that method definitely isn't one that we would want to use, and we would certainly want to use this property or that theorem that we just discussed where opposite angles are supplementary. So here's an example of where some student could go wrong in just using that first property where all 4 angles add up to 360. Here we're given an example where we're told that this quadrilateral could be inscribed in a circle. So even though it's not drawn in a circle, we're told it could be. So that means that opposite angles are supplementary. And so this student, maybe because it wasn't drawn inside a circle, or maybe because they didn't know the theorem, tried to set it up so that all 4 angles added up to be 360, but then they got stuck because there was 2 different variables. So this student kind of has a lot of issues going on. One being that if they were to use this method, they would probably want to substitute the expressions here correctly. And when you look at this statement, you'll notice some weird things. I don't know quite where some of these numbers came from, especially 114. That definitely doesn't come from combining any like terms here. So part of the problem is in the setup. If we were to try it out that way and correctly get to this step, it is a false statement to say that you couldn't solve for 2 different variables. If you've ever taken algebra, you know that that is possible. What we could do is solve this equation for x and then plug that expression in for every x term, and then our statement would be all in terms of z. Or we could instead solve for z, get an expression in terms of x and plug it in for z, and then we would have a statement with just x terms. So that's totally possible. Not easy, but certainly possible to solve. The best thing to do in this case for this problem, though, would be to use that theorem that says the opposite angles are supplementary. Set up an equation to solve for z, just using angles d and b, or set up an equation solving for x using angles a and c. Eventually you'll have to solve for both, but doing it separately makes it much easier. All right, so that's been angles inscribed in quadrilaterals in circles. Again, use that theorem that opposite angles are supplementary, and you should be able to solve problems that look like this.